class of this week, and in the previous class we have discussed pattern association, right? What is the importance of pattern association? What is its relevance in terms of the human biological brain processing of information in terms of associating things, right? And how that model of human brain ability to associate things, store and recall. Essentially, you associate things, then store, recall. So how can we do that? So associate, store and recall the patterns. These are the three fundamental activities. So this is what we were discussing in the previous class, right? In that regard, we said, look, there are two varieties of doing it, auto and hetero-association, right? So we have seen the auto-association. Then we have checked how auto-association can associate the patterns, store them and recall them, even when the input is noisy. Okay, that also we discussed. In fact, I asked you guys to do a couple of problems, right? Now we have actually done the auto association by taking a pattern and associating with itself. Then there is another aspect of auto association where multiple patterns, okay, multiple patterns in auto association. Okay, what do you mean by this? We said we can store, okay, we can store and associate and store S1, S2, S3 kind of a thing. Okay, so we can associate more than one pattern. Again, it is auto association. When I say more than one pattern, it is auto association. So more than one pattern are associated and stored. So how many such number of patterns I can store? Okay, number of such patterns. Imagine if I am able to store, say, S1 to say Sn. That defines the capacity of the network. Okay. So imagine if I am able to store 3 patterns. So in that regard, the capacity of the network is, remember, it is the 3, because I am able to store 3 patterns. Now there is a caveat here. Is it that I can store any of the 3 patterns and store them, and whenever I submit S1, I'm able to recall S1. If I submit S2, I'm able to recall S2, and submit S3, I'm able to recall S3. Okay, that is what actually I'm doing it. But is it that I can store any patterns? There is a caveat. Remember, the caveat is here is the stored patterns. Whatever the patterns that we are trying to store must be, there is a condition, must be mutually orthogonal. Okay, this is the fundamental criteria. If non-orthogonal vectors are tried to store, your network will not be able to function. Okay. So how do you say that the 2 vectors S1 and S2 are mutually orthogonal? If their inner product, the dot product, is 0. then they are mutually orthogonal, right? So if you have such type of patterns which are mutually orthogonal, only such type of patterns can be stored in the associative networks. This is one of the fundamental requirement. Okay, and we have already, I think we have discussed in the previous class that how do I store when I am having the multiple patterns? Obviously, imagine if you have three mutually orthogonal patterns, corresponding weight matrices, right? So the weight matrix to store S1 pattern, weight matrix to store S2 pattern, and weight matrix to store S3 pattern. This would be the cumulative weight matrix of your total memory. Okay, this is the total memory of storing three patterns. Okay, this is also we discussed in the previous class. Okay, is that clear? Is that clear? The point we discussed in the previous class is an extension. Okay, so in the previous class we talked that we can store a pattern, associate itself in the auto-associative memory, then recall the same pattern. And also, in fact, we discussed not only recalling the same pattern with the exact input, but also in terms of recalling noisy input that we discussed in the previous class. And today we said it's not only one pattern, but multiple patterns can be stored in the auto-associative network. Number of patterns we are storing, that defines the capacity of the network. The caveat here, the condition here is that whatever the pattern vectors you are trying to store, they must be mutually orthogonal. That means if you take any two vectors, their inner product must be 0. Only if those vectors that satisfy this condition can only be stored in the auto-associative, not only auto-associative, but for that matter, any associative network. Okay, and the corresponding weight matrix is the cumulative weight matrices of each of the weight matrix of the corresponding patterns. So this is the weight matrix of storing S1 pattern, and this is the weight matrix of storing. We have discussed in the previous class how these weight matrix can be calculated, and this is the weight matrix of storing S3 pattern. And cumulative W is now forms your memory, right? And then we have next, we have seen auto-association. The next one is hetero-associative networks. Okay, I remember I don't know whether we have discussed at length this thing. So the point is that you are going to store. The idea is that store the associations of the patterns. Store the associations between the pairs of patterns that are not identical, right? So S is not equal to T. This is what is hetero-association. So how do your network looks? The network looks in this way. Okay, just give me a moment. So is that image clear? You can see the image where the you have the S pattern from X to Y. So you are trying to associate the S pattern from X to Y layer, and this is the T pattern from so X to Y layer. So this is the T pattern in the Y layer. So you are trying to associate both S and T where S is not equal to T. Right. So this is the typical architecture of your hetero-associative memory. Is that clear?
Yes, sir.
So let me show you the another this one, the algorithm. Okay. So let us have the look at the algorithm. So the algorithm is fairly simple. Okay, the algorithm goes like this. Imagine if your S pattern is this. S is equal to say S1, S2, and so on, Sm, and your T pattern is T1, T2, and so on, Tn. Okay. Then your weight matrix either can be calculated through the Hep's rule or else through your outer product of the matrices. So S transpose T would be your weight matrix. So that means so S1, so on, Sm, and T1, so on, Tn. So this is m cross 1, this is 1 cross n. The resultant weight matrix will be of m cross n. Okay. Now the point is, can I store multiple patterns of in the hetero-association? Yes, of course. I can store S1 and T1, S2 and T2, and S3 and T3. How can I do it? So I calculate W1, this is for W2 and W3, and my weight matrix would be W1 plus W2 plus W3. Is that clear? This is the hetero-association. So please remember the book contains the problems for each of these stuff. So I suggest you guys to have a look at it. Let me take one particular case where imagine your S is S is 1 minus 1, 1 and minus 1, and T is minus 1, 1 and minus 1. Okay. Now you guys can try with calculating the weight matrix W1. So you are going to associate S1 with T1. Then you can try multiple things. Number one, so first calculate these things. Number one, W1. Number two, provide input, which is S1 to the weight matrix, and see what is the output you are getting. Similarly, give noisy S1 and see if the network is able to recall the T1 even though you are submitting the noisy S1. So you change the bits of S1 and then try with the S1. Okay. Is that clear?
Sir, what is that alpha S1? Is it directly proportional? What is that symbol?
Which one? Where?
S1 alpha T1, like
Where is alpha? I have not
alpha.
written alpha.
Is it,
This
sir?
one. This one.
Above W1.
This one.
Yes, sir. Yes, sir.
Yeah, no. This is actually okay. This is actually I was trying to write and. Okay, so this is as pattern. This is T pattern. That's it.
S1 and T1.
Yeah. I was trying to write and here. So this is not alpha. Okay. So this is your weight matrix calculation. Either you can do through Hebb's rule or outer product rule. Okay. So this is about hetero-associative network. So please look at the small problem I have given and try that at background, either off the class on the, and then also try for the weight matrix calculation, submit S1 and then perform the noisy S1, those things. And similarly, you can even try for multiple patterns. You have a look at the book back exercises and solid examples, wherein which you have the questions by giving multiple patterns, and the network is trying to store by calculating the corresponding weight matrices and calculating the overall weight matrix and submit the any input, either say take an example S2 and see if the network is able to recall it. Okay. So the next one is bidirectional associative memory. Okay. Again, this is also on the similar lines of associating the patterns. I hope you guys remember the just a small example that I've narrated in the previous class, where I said if you are trying to recall soft computing, after some time, you have certain patterns that you get. Like somebody said fuzzy logic, somebody said that network training, so kind of a thing. So you give the word soft computing, you are trying to recall some patterns associated with it. The bidirectional associative memory is going to work in the other direction also, in the sense that imagine, the one example, typical example I said was, imagine you meet after some time and trying to recall about soft computing, then somebody may say that, okay, Aswani Kumar, so you are going to recall about the faculty. Now it is like the other way around. Imagine if the faculty name is pronounced, oh, Aswani Kumar, he has taught us soft computing. So it is like the other way around. So you connect soft computing, associate the soft computing with the faculty. That is what we discussed about auto-association and hetero-association kind of a thing. Now the bidirectional is about bringing the other direction also, in the sense that you are going to connect from the output to the input. Okay, so let us see how the network looks.
Sir,
Yeah, please.
sir, in the previous question you gave, I am not getting the same output even for the like not noisy output. For the same input, I am getting different answer.
1 minute. Okay. I'll come to that. So let us take the bidirectional associative memory. I hope you guys are able to see the. Oh, I think I have copied the wrong diagram. This is the problem. Slide. Okay. Yeah. So this is the one. Okay. Now you look at it. The input layer. This is generally X layer, the input, and this is the output. That's what we do. Now, if you notice the bidirectional associative memory, if you notice, you can see the activations in the forward direction and also in the backward direction. So you can see the arrows coming back, returning back. So this is x2y, and you have y2x as well. Okay, you can notice the arrows directions, right? So it is basically a hetero-associative model. Okay, and it is basically a hetero-associative model where you are having the two layers of network, two layers of nodes interconnected in bidirectional path. Okay, so you can see the bidirectional path. So you have path from x to y, and you have the path y to x. Okay, so that means you are going to associate the patterns S and T. Okay, this is not alpha here. This is S and T, and by associating in the bidirectional, you submit either S as a stimulus and get the response as T, or else submit T as the stimulus and get the response as output, or the response, S as the response. Okay. Now, the point is, we all know that when you are associating S with T, the weight matrix is W, right? When you are performing the bidirectional association, that means the reverse association, the weight matrix would be weight W transpose. That's what, if you can notice here, when your pattern association X to Y, the weight matrix is W. Pattern association Y to X, the weight matrix is W transpose. That means when if you calculate W, that is sufficient enough, and when you are giving the stimulus Y as an input, that means T as an input, you are supposed to use the weight matrix W transpose for recalling the patterns. I hope you guys are able to follow. Are you able to follow? So when I am using S to T, my weight matrix is W. So calculate W. You need to calculate W, then give S as stimulus, get T as output. In the case of reverse, you are going to have T to S. You have to calculate W transpose, then give T as stimulus, get S as response. Okay. Remember, your S and T can be binary or bipolar patterns. Remember, typically you will have bipolar only. Bipolar is preferable. That brings the lot of generalization concepts. Okay, generalization ability. And in addition to that, I hope you guys remember the weight matrix should have what on the principal diagonal? What it should have on the principal diagonal?
0.
It should be 0. So the weight matrix, whenever you are calculating, the principal diagonal is supposed to be the zeros.
Sir, is it true even for hetero-associative?
Yeah, can you please repeat? What is the question?
Sir, is it also true for hetero-associative?
See, whether it is auto-associative or hetero-associative, or whatever the associative memory you take, what is the principal diagonal cells indicate in the weight matrix? They typically indicates connections to the self, connection to that particular node itself, right? When it is indicating connections to the node itself, that means it is supposed to be the 0. Okay.
So, but if our matrix is M is to N, then it won't have a principal diagonal.
I'm talking about the auto-associative and hetero-associative.
Yes, sir. So for the square matrix, we have that, but in the rectangular matrix, we won't have any.
When you are talking about the, say, that's what, when you look at the, okay, let us go to the question that you have raised about the, the hetero-association. Okay, just. Okay. So yeah, let us come to this particular question. You talked about this S1 T1, right? Somebody said. Hello? Oh. Am I audible here?
Yes, sir.
Yes, sir.
Yeah.
Audible.
Yes, sir.
Yeah, yes. Very good. So the point is, now look at the S and T here. Okay. So what is the weight matrix you got?
So for the previous question.
Yeah. That's what somebody asked me this question.
One.
Somebody has said that they are not able to get it.
Yeah. Yes.
So that's why.
Yeah. -1, 1, -1.
Okay.
And 1, -1, 1. And -1, 1, -1.
Okay.
And then 1, -1, 1.
Yeah, that's all. So this is what exactly is the weight matrix. Okay. So now you need to verify whether you are, whatever the network that you have got is the one is able to classify or is able to recall it or not. So you provide the input as the pattern, wherein which the net input to the pattern, which is what is the net, so take S pattern S1 into W. So what you get, 1 minus 1, 1 minus 1, and then W. What you get?
Sir, I'm getting -4, 4, 4, and -4.
Exactly. -4, 4, and -4, right?
-4, 4, -4, 2 4s, and -4 again.
-4.
4, 4, and -4.
-4, 4.
Again 4 and -4.
Okay, that means, okay, let me write it like this. -4, 4, 4, and -4. That's
Yes.
what you are getting. Can you guys please check and then let me know? See, this is what is your S pattern? What is your S pattern?
1 -1, 1 -1.
1 minute. It is 1 into 4, right? And
yes.
What is your W pattern? 4 into 3.
Yes.
This is supposed to be 1 into 3. How do you get 1 into 4?
Yes, sir. That 1 4 won't exist. Yes.
Yeah. So you apply the activation rule as per the algorithm that what we have discussed, right? So when you apply that, then obviously you will be getting the stored pattern. Okay. Now coming back to the your bidirectional associative memory, when I was referring to the weight matrix in the auto-association, when your weight matrix is a square matrix, obviously your principal diagonal will have the self node connections as zeros. Okay. Now let us take the case of bidirectional associative memory and then try with one particular example, which is 25.
Sir.
Yeah, please go ahead.
So in that example, we didn't get the same input, so it means that the weight function that the weight matrix we are getting cannot store anything, or what?
No, you got the pattern, right?
Sir, we got. So we provided 1 -1, 1 -1 as input, but got -1, 1, and -1. Oh, okay. I got it.
Sir?
Yeah, you associated S with T, right? And
Yes,
T
sir,
you got it.
I get
Yeah,
it now.
yeah. Go ahead.
So in the last slide, like how we got -4, 4, -4, like I understood that multiplication to get W. Then how we got -4, 4, 4 -4.
Yeah, it's a typical, this one. This is typical, your typical matrix multiplication. No, yeah. Okay,
Sir,
so
we got W by multiplying S transpose and T, right?
Sorry.
We got W by
Correct.
multiplying S transpose
This
and
is
T.
the W you got or not? You tell me. You look at the W that is written here. This is the W you got or not? Yeah,
Yes,
you
sir.
please check that. Please check that. Okay. So now have a look at one of the interesting problem, wherein which there are two patterns called E and F. Two alphabets are patterns. Okay. The way they are given. Look at the way the E and F were given. So you can see stars and dots. Okay, you can see stars and dots. Now the point is the stars are regarded as 1 and the dots are regarded as -1. So that means your E is going to be 1, 1, 1, 1, -1, -1, 1, 1, 1, 1, -1, -1, 1, -1, 1. Okay, and the similar way to the sorry, this is also 1. Okay, so 1, 1, 1, all stars 1, stars are 1, dots are -1. So this is 1, -1, -1, 1, 1, 1, 1, -1, -1, and 1, 1, 1. This is what is E pattern. Okay, and then the target given for E is -1, -1. Okay, this is the target. So for F, the target is given as 1. Okay. Now the problem is asking you to calculate the BAM network. Okay. Calculate the BAM network. Associate your E pattern with -1, 1 and F pattern with 1, 1. And when you present a E pattern and calculate W, then present E pattern, get -1, 1, present F pattern, get 1, 1. Okay. So you can see this particular problem given in the book, okay, which is a solved out example. In fact, the entire E is written as the pattern vector. Okay, what is the pattern vector of E? So 1, 1, 1, 1, -1, -1, and so on. Okay. Similarly for F, the pattern vector is given as 1, 1, 1, again 1, 1, 1, 1, -1, -1, and so on. 1, -1, -1, and 1, -1, -1. So you write the pattern vector as 1, 1, 1, and then again 1, 1, 1, 1, -1, -1, and so on. Okay. So once you write that, now you calculate W1, which is E transpose T, imagine this is TE and this is TF, target F. E transpose TE, similarly W is W second weight matrix is F transpose TF. Then your weight matrix, then present E to W and get 1, -1 and 1. Similarly present -1 and 1 to, when you are presenting minus and 1, you will present it to which matrix? The bidirectional.
Sir, to E.
What? W transpose. Correct? See, when you are presenting -1, 1 as a stimulus, you will present it to the which matrix? The W transpose matrix, because you are presenting in the reverse direction, and get your E. Similarly. Yeah, please.
So we had quiz at 6:35, right?
Yeah, you want me to continue or you want to write the quiz?
No, sir, you can continue if you want.
Yeah. So let me continue. Huh? You want quiz? Okay, you will get it. So F to W, get 1, 1, then present 1, 1 to W transpose and get F. So please do this. You can see from the book and it becomes a practice to you about the bidirectional associative memory. Okay. So any doubts with regard to the BAM? We discussed the auto-associative and multiple patterns, hetero-associative, multiple patterns, and then BAM network. Okay. So for your better understanding, I am giving here the typical BAM network algorithm. So that will be helpful to you. Fifth. So this is your BAM network procedure where you are initializing the activations, then you are calculating the net input. How you are calculating is through typically by multiplying the inputs to the weights, and remember this is through the Hebb's rule. Okay, in fact we have achieved it through the outer products. Okay. And similarly, this is for reverse. This can be calculated through the weight transpose. Okay. That's all with regard to BAM. And please solve the book back exercises. Then we will go for the quiz. Okay. Let me once stop recording.